In 1905, Albert Einstein discovered that mass is actually congealed energy. Mass and energy are two sides of the same coin, as stated in his celebrated equation, E equals mc squared. In this equation, E stands for the energy that any mass has at rest, m stands for mass, and c is the speed of light. The quantity c squared is the proportionality constant of energy and mass. Some people misinterpret this to say that mass travels at the speed of light squared. Not at all, for as said, c squared is the constant of proportionality. As an example, in the geometry equation, c equals pi d, we don't say that d is moving at pi. The proportionality constant c squared nicely converts kilograms to its equivalent in joules. E equals mc squared is the key to understanding why and how energy is released in nuclear reactions. This drawing of Einstein, by the way, is by San Francisco artist Mary Chu, my former student. Very nice. An important fact: the more energy that is stored in a particle, the greater is the mass of the particle. Another fact: the mass of a nucleus is less than the sum of the masses of the nucleons that it contains. Both of these facts are powerful statements. To make sense of them, consider the work required to separate nucleons from a nucleus. Recall that work is expended energy equal to force times distance. Think of the amount of force required to pull a nucleon out of the nucleus through a sufficient distance to overcome the attractive strong nuclear force, as Stanley's strongman indicates. Enormous work would be required. What becomes of this work? This work is energy added to the nucleon that is pulled out. Or said another way, in terms of E equals mc squared, the extracted nucleon has more mass. Which brings up the question, how can we measure the mass of atoms, let alone nucleons that make up atoms? One means of doing this is with a mass spectrometer. In a mass spectrometer, charged ions with identical speeds are directed into a magnetic field where they deflect into circular arcs. The greater the inertia of the ion, the more it resists deflection and the greater the radius of its curved path. The magnetic force sweeps the heavier ions into larger arcs and lighter ions into smaller arcs. The ions pass through exit slits where they may be collected or they may strike a photodetector. An isotope is chosen as a standard and its position on the detector is used as a reference point. The standard is the common isotope of carbon, carbon-12, the atomic mass of which is assigned the value of 12.00000 atomic mass units. Recall that the atomic mass unit, AMU, is defined to be precisely 1/12 the mass of the common 12 atom. With this reference, the AMU values of the other atoms are measured. Although we have no way of measuring the masses of individual nucleons within the carbon-12 atom, we know that the average mass per nucleon is exactly 1.00000 AMU. And to be precise, this includes also the tiny masses of the atom's 6 electrons. This is less than the mass of either a hydrogen atom, a proton and electron, or a lone neutron, which are, respectively, 1.007825 and 1.00867 AMU. Again, a collection of nucleons has more mass when isolated than when locked inside an atomic nucleus. Yum physics. Here's a graph of nuclear mass as a function of atomic number, that is, the number of protons. As we'd expect, the graph slopes upward with increasing atomic number, which simply indicates that elements are more massive as atomic number increases. Note that the line in the graph curves. That's because more massive atoms have proportionally more neutrons. Recall that neutrons act as a nuclear cement needed to keep nuclei, especially larger nuclei, together. A more important graph results from a plot of average mass per nucleon for the elements hydrogen through uranium. This is perhaps the most important graph in any study of nuclear physics. It's the key to understanding the energy associated with nuclear processes, radioactivity, fission, and as we shall see in the following lesson, nuclear fusion. To obtain the average mass per nucleon, you divide the total mass of an atom by the number of nucleons in the nucleus. Again, for precision, we include the tiny masses of the electrons. In a similar way, if you divide the total mass of a room full of people by the number of people in the room, you'll have the average mass per person. The major fact to learn from this graph is that the average mass per nucleon varies from one nucleus to another. Very important. Nucleons lose mass when they join together to form nuclei, and how much they lose depends on which nucleus they form. Again, for emphasis, very important. The greatest mass per nucleon occurs for hydrogen, whose lone central proton has no binding energy to pull its mass down. As we progress to elements beyond hydrogen, we see that mass per nucleon decreases and is least for iron. The iron nucleus holds its nucleons more tightly than any other nucleus does. Beyond iron, the trend reverses itself as proton repulsion becomes more important and the binding energy per nucleon gradually decreases, meaning that the mass per nucleon gradually increases. This continues all the way through the list of elements, and this graph cuts off at uranium. Can you see from this graph why energy is released when a uranium nucleus is split into two nuclei of lower atomic number? Look at where such fragments fall in the curve. They lie about halfway between the masses of uranium and hydrogen on the horizontal scale of the graph. So what does this tell you about the mass per nucleon in the fission fragments? Can you see it's less than the mass per nucleon when the same set of nucleons is combined in the uranium nucleus? Is this making sense? I hope so. Now here's the interesting part. First, recall that when a uranium-235 undergoes fission, some 200 million electron volts of energy are released. Well, when the decrease in mass of the fission fragments is multiplied by the speed of light squared, it equals 200 million electron volts. That's the energy yielded by each uranium nucleus on average that undergoes fission. How nice how all this ties together. Yum physics. And as mentioned earlier, most of this energy is the kinetic energy of the fission fragments, elements such as krypton and barium. We can think of the mass per nucleon curve as an energy valley that starts at the highest point, hydrogen, slopes steeply down to the lowest point, iron, and then slopes more gradually up to uranium. Iron is at the bottom of the energy valley, where it has the least mass per nucleon. And I should add, the most binding energy per nucleon. This means that more energy per nucleon is required to pull an iron nucleus apart than for any other nucleus. Take a moment to study this curve, maybe with your pause button. All nuclear power today is by way of nuclear fission. A more promising long-range source of energy is to be found on the left side of the energy valley. That's nuclear fusion that we'll cover in the next lesson. For now, I want to leave you with a question. A particular element in the periodic table has a nucleus that is composed of protons and neutrons having minimum average mass. Name that element. Until next time, good energy.